Hi all, the topic I want to discuss with you today is the center of mass. Now we're talking about the center of mass within a plane that we have infinitely many weights within the plane. But before we talk about the calculus standpoint of center of mass, I first want to go back to what you've probably done in a physics class before when you talked about center of mass. Let's assume that the XY coordinate plane is just a weightless plane, but then you're going to put three weights on it, and I have one in quadrant one, one in quadrant two, and one in quadrant three. The one in quadrant one here is at the location 3, 4, and it's a 5 kilogram mass. I'm going to put a 2 kilogram mass in quadrant two at the location of negative 8, 2, and a 3 kilogram mass in quadrant three at the location of negative 3, negative 6. Okay, now, if those are the only three weights in the plane, I want you to find the point in the plane that would balance the weights of these 3 points. You'd say, well, okay, then you need to find the average x value and the average y value. The way that you would do that is you would say, well, the average x value is going to be the summation of all of the products of the distance times the weight from, or the distance from the axis, and then times the weight. So this x value of 3, well, it's a distance of 3 units from the y-axis, and the weight is 5. So I would say, well, 3 times 5 for that first one. Now for the next value that's going to give me the average x value, I would say, okay, distance from the y-axis is the x value, negative 8 times the weight of 2. My last one is a distance of negative 3, again, just indicating it's to the left of the y-axis, times the weight of 3. So I take all of those distance times their corresponding weight, and then please notice what I'm dividing by. I'm dividing by the sum of these three weights, or the sum of these three masses, 5 kilograms plus 2 kilograms plus 3 kilograms. When I do my numerator, it's just 15 minus 16 minus 9 for negative 10. My denominator is positive 10. This gives me that the average x component within this region, if these are the only three masses in here, is at an x location of negative 1. Now, one other point I want to drive home here is that this numerator here, that's measuring the sum of all of the distances times the mass at that distance, these are called the moments about the y-axis. Subscript, or sorry, we would use the notation m sub y for the moment about the y-axis there. Now, whenever we're trying to find anything about the average x value, it's always the moments about the y-axis. The distance you are from the y-axis is always x, and then that distance is multiplied by the amount of mass at that distance. So you say, okay, the distance times the mass at that distance, the sum of all of the weights in the scenario, all of that together would be the moment about the y-axis. But then to get the average x value, you say, well, yeah, I need to take the sum of all of those, but I need to divide by the sum of the masses. That's all I've done down there to get that average x value of negative 1. And that makes sense to us. You wouldn't just say it's negative 10. Clearly, the average x value isn't to the left of all x values in the plane. That's why we have to divide by that denominator to get the much more reasonable answer of negative 1. Similarly, if I wanted you to find the average y value, you'd say, well, all right, then the average y value for this first one, I can say, well, the y value is 4. The mass at that point is 5. 4 times 5. The next one has a y value of 2 times a weight of 2. The next one has a y value of negative 6 times a weight of 3. Now, in all of these y values, that's just the distance you are from the x-axis, and then you're multiplying that by the amount of mass at that distance. The sum of all of those values, please keep in mind here, is called the moment about the x-axis, and we would call that m sub x. Sometimes it confuses students when they see that the average y value is the moment about the x-axis divided by the sum of the masses, but that's precisely what it is, because any y value, it's just the distance a point is from the x-axis. That's why we say it's the moment about the x-axis. All of these distances times the mass at that distance, the sum of those, the moment about the x-axis. We divide that by the sum of all the moments, and you can see our average y value in this case is 3/5. So if I put my finger right here in the plane and I held it up, it should balance it out perfectly if these are the only three weights acting on that plane, and the plane would be completely weightless otherwise. Now, from that finite scenario from physics, I want to explain where our calculus formulas comes from. So in calculus, we're going to have some region f of x that we're trying to find the center of mass of. So similarly, whenever we try to find the center of mass, you say, well, okay, how are you going to find the average x value of any region? You can say, well, okay, the average x value, that's just the distance you are from the y-axis times how much weight is at that distance. Well, now we really don't have weight necessarily, but you do have the amount of the curve at any point. So if I have this curve f of x and I'm trying to find the centroid or the center of mass of that region, and you can see that's our two terminologies for this center point. Sometimes it's called center of mass, other times it'll be called centroid. Your book frequently also uses the abbreviation just capital COM for center of mass. But now, if I wanted to find the center of mass of this region, then all I would say is that, well, the average x value, it's going to be the distance you are from the y-axis, which we already know is whatever x is, times the amount of the curve at that region. So you'd say, well, the weight of that point is just the amount of whatever rectangle this point would be the center point of here. And so I could say, well, the area of that rectangle is just going to be the height times the width, f of x times delta x. Now, please keep in mind, the higher the function is, the more that x component will weigh than other x components where the function is really small. So I could say, all right, then the moment about the y-axis is the summation of the distance you are from the y-axis, which is defined to be x, times how much material or weight is at that point, and that's going to be given by f of x delta x. So this is in our series notation, and you would just sum up all of these rectangles from where they begin to where they end, and if you wanted a perfect representation, you'd have to do infinitely many of them. But now, just like up here, you can't simply just say it's the moment about the y-axis. You're going to have to divide by the sum of the masses. Well, what's the sum of the masses of this area underneath f of x? You just say, well, it's the summation of all of the rectangles within theirs, and you just say, well, that's the summation of f of x delta x from 1 to n. Now, in integral notation, which is what we're going to be using, you would just say, then this numerator, you're going to sum every rectangle starting at where you're first interested in to where you're to the last point of interest. We always just call that the integral from A to B, the first point of interest to the last point of interest of your formula, x times f of x dx, as those rectangles become infinitesimally small. Of course, our denominator is going to be the integral from A to B of f of x dx. Now, when I talk about the average y value, you'd say, well, okay, if I'm trying to think about what the average y value of this region is. In order to determine the average y value, you go in and you can say, well, I know that the average y value is just going to be a distance from the x-axis. And we'd say, well, the average y value of any rectangle, no matter whether I chose the f of x over here or over here, the average y, it's just going to be 1/2 of whatever the height of the rectangle of the curve is at that point. And we can see that the overall height of the rectangle is just whatever our function f of x is. So half of that is going to be 1/2 f of x. You could say, well, that's representative of the distance, the average distance in this rectangle you are from the x-axis, times the amount of material in that, or at that point. You just say, well, that's the area of the rectangle, which is f of x delta x. That's where this formula comes from. This is the average y value distance. And why can't you just say y here? Because you need it in terms of x. So that's why I had to call y equal to 1/2 whatever the function is. And then the area of the rectangle at that point is your f of x delta x, divided by the summation of the sum of the masses, f of x. Ooh, and that should be a delta x there. It turns to dx in the next step. Now, my numerator here is going to be 1/2 the integral from a to b of f of x quantity squared with respect to x. Now, let's see how that works in action. Sometimes students get a little overly concerned that they're not quite sure where these formulas come from. The actual use of these formulas is pretty straightforward in problems. Notice here, if I ask you to find the centroid under the linear function f of x is equal to 6 minus 2x, and I'm wanting you to find the centroid from 0 to 3. All right, now you can already see I have the answer figured out, but if you were just guessing here in this region, common sense is going to let you understand that the average x value has to be closer to 0 than it is 3, because there's more function over here than there is down here. Similarly, the average y value also has to be closer to 0 than it is 6, because there's more values down here than there is up towards the top. That's why the centroid is going to be at 1, 2 here. But now let's see where that came from. So first thing I did in order to find the centroid, first thing I said, well, I know that the average x value is going to be the moment about the y-axis divided by the sum of the masses. The average y value is the moment about the x-axis divided by the sum of the masses. Well, the sum of the masses here in this problem, that's just your integral from where it starts to where it ends of f of x dx. So I just plug that into my formula. Easy power rule here. I get 6x minus x squared evaluated from 0 to 3. I plug the 3 into that and I get 18 minus 9 for 9. So I can say, well, the area under this curve, which is going to serve for the mass of this region, is 9 units. Now, if I talk about the moment about the y-axis, I can say, okay, the moment about the y-axis, that's the distance from the y-axis times the amount at that point. So you say, oh, that's the x times f of x in there, which you see right up here. And I can say, well, all right, I have x times f of x, x times 6 minus 2x, integrating that from 0 to 3. I distribute through the x and I get 6x minus 2x squared. We now use the power rule. That'll be 6x squared over 2 for 3x squared. And then I'll get 2/3 x cubed. We evaluate that from 0 to 3. When you evaluate at 3, you'll get 3 times 9 is 27 minus 2/3 times 27. That's going to be 27 minus 18 is 9. So now instantly I can already say, well, I already know what my average x value is. It's the moment about the y-axis divided by the sum of the masses. It's 9 over 9. That's where I got my average x value down there for an answer of 1 here. Now, in order to get the average y value, I just say, well, it's the moment about the x-axis. And I can say, well, all right, the moment about the x-axis, it's the average distance any particular point is from the x-axis. And you say, well, that's just going to be half of the function's height times the amount of material at that point, which is f of x dx. So we get our formula. That's where all of this came from. The 1/2 f of x quantity squared integrated with respect to x. From this step to this step, I had no choice. I needed to go ahead and square that group out. So I did the algebra before I did the calculus. 6 minus 2x raised to the second power gave me 36 minus 24x plus 4x squared. Then from that point, I just used the power rule to get 36x minus 24x squared over 2 for minus 12x squared, and then plus 4/3 x cubed. We evaluate that from 0 to 3. And the only thing I did was I evaluated it at 3. Obviously, when we evaluated at 0, we'll get a 0. When I plugged in a 3, I got a 36. You need to remember the 1/2 out in front. 1/2 times 36 gave me the moment about the x-axis was 18. Now, that led me to know that, well, then the average y value is the moment about the x-axis divided by the sum of the masses. 18 over 9 gave me an average y value of 2. Thus, I could say the centroid, or otherwise known as the center of mass, is x bar, y bar at your ordered pair 1, 2. Now, I think you'll find that most of the problems are pretty straightforward. Sometimes it's going to require slightly harder integration techniques in the evaluation of it and stuff. But as long as you remember these formulas, it should be pretty straightforward here. We look at one more problem here with you. For this one, I'm asking you to find the centroid under the natural log function from 1 to 3. So I specifically want the region above the x-axis, and I want to find the center of mass of that region. It starts off here, we know the natural log of 1 is 0. If you plug the natural log of 3 in there, it's asking you what power would you have to raise e to get a 3. It's like 1.09. So we're going from 1, 0 to 3, 1.09 here, and we're asking what the center of mass is. Now, I put the exact answers down here for the x and y, but just thinking logically here. If I said, well, do you think the average y value is closer to 0 or closer to 1.09? There's no question. It has to be closer to 0. It has to be, because there's more points down here closer to 0 than there are points close to 1.09. So if I had to make a ballpark guess as to what this value is, I'd say it's probably like 0.45 or something. So I'd say the average y value, it's certainly less than half of 1.09. Half of 1.09 would be 0.545, which there's still more points below that than above that. So I'd say it's probably more like 0.45 or 0.5 at most. Now, the average x value, would you say it's closer to 1 or closer to 3? Again, there should be no question. It's closer to 3. Why? Because there's more points in this region between 2 and 3 than there is in this region between 1 and 2. So if I had to try to find the average x component, common sense dictates it's probably like 2.2 or something like that, 2.1 at least. And I could plug this in and find out that decimal, which I didn't bother to do because I would always prefer exact answers. But sometimes it's kind of interesting to think about where the center of mass would be. Now, let's get to the problem here. In order to determine center of mass, you only need 3 things. You need the sum of the masses, you need the moment about the y-axis, and the moment about the x-axis. So the sum of the masses is just the integral from where the region begins to where it ends of your f of x dx. So the integral from 1 to 3 of the natural log of x dx. Now, hopefully, you've integrated the natural log enough to have it memorized as x ln x minus x. Technically, if you don't have that memorized, it would be a very simplistic integration by parts problem where you let u equal the natural log of x and du is 1 over x. dv is dx and v would be x, and it would integrate to be x ln x minus the integral of 1 dx, which then becomes minus x. Now, I went ahead, since that should be something that we already have ingrained in our memory, I just went ahead and did it without the integration by parts. We're evaluating that from 1 to 3. When I plug in the 3, we'll have 3 natural log of 3 minus 3. When I plug in the 1, we know natural log of 1 is 0, so the first term cancels, but I'll still have a minus 1 there. So minus a negative 1, that's going to give me 3 natural log of 3 minus 2. So that's going to be the sum of the masses of this entire region here. Now, for the moment about the y-axis, so I can say, well, all right, that's going to be helpful, moment about the y-axis, that's going to be helpful in determining the average x value. So you'd say the moment about the y-axis, it's the distance you are from the y-axis times the amount of material at that point. Well, the distance you are from the y-axis is x, and then times the material, well, that's the natural log of x dx. So the moment about the y-axis is just x times our function f of x, the natural log of x, integrated again from 1 to 3. Now this one, I did go ahead and show the integration by parts. It's a little bit more challenging. We'll have u is equal to the natural log of x, du is 1 over x dx. So therefore dv is my x dx, and when you integrate x with respect to x, you get x squared over 2. So now, I can say integration by parts says that the answer is going to be u times v. So I said 1/2 x squared natural log of x minus the integral of v du. That gave me minus 1/2 the integral. X squared times 1 over x just gave me an x in there. And you'll notice I tried to keep my notation well because I just said all of this group eventually needs to be evaluated from 1 to 3. Now, when I integrate x, that's going to give me a 1/2 x squared, multiplies the existing 1/2 to give me minus 1/4 x squared. Now I do evaluate all of this group from 1 to 3, and I did that below. I said the moment about the y-axis here is going to be 9 over 2 natural log of 3, and then I would get minus 9 over 4. When you plug in the 1, all the first term cancels because the natural log of 1 is 0. But the last term, you're still going to have a minus 1/4 times 1. Well, that's going to give you, you're subtracting because it's the lower limit of evaluation, and then it's a negative inside. Minus a negative 1/4 gives me plus 1/4. That's going to cancel out with one of these minus 9/4 and gives me minus 8 over 4, which is just minus 2. So I can say that's a simplified moment about the y-axis answer there. So I have my sum of the masses, I have my moment about the y-axis. Last thing, and typically it's usually the most difficult to find, the moment about the x-axis. The moment about the x-axis is always 1/2 the integral of f of x quantity squared dx. Well, here's your f of x, so it's the natural log of x quantity squared dx. I knew I couldn't integrate that by normal methods, so I used my integration by parts again. Let u equal the natural log of x quantity squared. Du, you have to use the chain rule here. 2 comes down in front of the group, times the group to the first, times the derivative of the inside, which is 1 over x with respect to x. Now dv has to just be the dx, the 1 dx. If you integrate 1 with respect to x, you get back x. So now, integration by parts is going to say my answer, and I remember I have my 1/2 out in front of that. You have to remember that. And then on the inside, it's u times v, x, the natural log of x quantity squared, minus the integral of v du. So this x and this 1 over x cancels. You'll notice I brought the 2 out in front and then have the integral of the natural log of x dx. Well, we already know, or we should already know, that the integral of the natural log of x dx is x natural log of x minus x. So I just went ahead into this step, substituted that in its place. You'll see I have everything else remaining. The 1/2 times the group, this is my original u times v, and then I have minus 2 times the integral of the natural log of x, which is right here. Now, in the evaluation portion here, or right before I evaluated, I wanted to distribute that 1/2 to get 1/2 x natural log of x quantity squared. Then that 1/2 just canceled out the 2, and I have minus x ln x plus x, evaluated from 1 to 3. Now when I evaluate at 3, the first term you'll get 3 over 2 natural log of 3 squared, minus 3 natural log of 3 plus 3. So really nothing I can simplify there because all of these first 2 terms are irrationals, and I'd much rather have an exact answer. My lower limit, I subtract it, and when I plug in the 1, the first and second term just cancel out. Your third term, of course, is going to become a 1, which you then must subtract since it's your lower limit of integration. So when I subtract that, it just makes the plus 3 a plus 2. I keep my first 2 terms the same, and I have my simplified moment about the x-axis. Now you say, okay, then what is the average x value every single solitary time? It's the moment about the y-axis divided by the sum of the masses. So it's just your answer here, divided by the original sum of the masses. The average y value, it's the moment about the x-axis that we have right here, again divided by the sum of the masses, the 3 natural log of 3 minus 2. All right, guys, I think you'll find the problems in this section pretty straightforward, very similar to these two. There's not many, I think maybe 5 problems in the assignment, but let me know if you have any trouble. I'll be glad to help.